Hi all, welcome to the next topic of Unit 1, Logic Microoperations. So coming to the contents, we are going to see the introduction to microoperations, what are the list of logic microoperations and their hardware implementation. So in the introduction, logic microoperations are nothing but they specify the binary operation for the string of bits which are stored in the registers. So here in these operations, each bit of a register is treated separately and the operation is being performed on the each bit of a register. So for example, if you consider the exclusive OR operation of for the two contents of the two registers R1 and R2, it can be represented as R1 XOR R2. This is an XOR symbol. So this particular operation performs an XOR operation on the contents of two registers R1 and R2, treating each bit of the register separately, and the result is stored in the register R1. So if you see this is a control function P, which means that when this particular function P is equal to 1, if the control condition is satisfied and P is equal to 1, then it performs a logical operation, XOR operation on the contents of two register, and the result is placed in register R1. So coming to the list of logical microoperations, there are 16 different logical operations that can be performed on two binary variables x and y. So if you consider two binary variables x and y, there are four possible combinations 0, 0, 0, 1, 1, 0, 1, 1. So on these two binary variables, there are 16 possible different logical operations possible, which are represented from F0 to F15. So this is the table for the 16 logic operations which are represented from F0 to F15. So if you look at this particular table, there are four basic operations, logic operations that are used based on which the other 12 logic operations are derived. So which are nothing but AND, OR, NOR and complement. Using these four logic operations, all the remaining 12 functions have been Boolean functions have been derived. So let us look at each functions. F0 is equals to 0. So if you look at it, each function is represented with the equal to operator, and it performs a function on two Boolean variables x and y. And this is a micro operation. So x into y, if you see this function x into y, it can be represented as a, x is represented by a and y is represented by b. So it performs an operation a and b. So as we already know, there are three types of four operations: and, or, XOR, complement, right? So using these, we are going to perform all the remaining operations. So f is equal to 0 means that the function use 0, clear, it performs a clear operation. So if you look at the truth table for this particular function f0, the particular result is cleared. So the contents of f0, all the combinations will be cleared to 0. So that is f0. Coming to f1, it performs x into y, xy. So that is represented in the form of a micro operation as a and b. So it performs an and operation on the contents of a and b, or x and y. So as I hope you already know the truth tables for logical operations and, or, not, nor, XOR and all. So not is nothing but a complement operation. So if you look at the truth table of and, it can be represented as a into b or ab. So whenever the values of a and b are 1 1, the result becomes 1. For all the remaining conditions, the result is 0. So similarly, based on that, so whenever it is 1 1, the output is 1, where for all the values it is 0. So this is how the Boolean function is performed. let's see the next one, F2. It is X and Y complement, which means that A and B complement. So first we are going to perform Y complement and then performs an AND operation with the value of X. So if you look at the truth table, so 0 and Y complement is 1, 0, 1. So 0. And here 0, 0. So 1, 1, 1. Complement. We are doing a complement of Y. 1, 1. It becomes 1. And 1, 0. It becomes 0. So we are first doing a complement of Y and then performing an AND operation between X and Y. Y complement. So this is F2. Similarly, F3, it just takes the value of X. So for F3, whatever is the value of X, that is the output of the truth table. So 0, 0, 1, 1. That is nothing but the value of X. And coming to F4, it is X complement Y. So it is, we are going to do a complement of X and perform an AND operation with the contents of Y. So it becomes 1 and this is 0, 1, 0. So 0. Here 1, 1. So 1. Here 0, 0. It becomes 0. Here 0, 1, 0. So that is how F4. Next coming to F5, it simply takes the value of Y. So whatever is Y, 0, 1, 0, 1, that is your output, 0, 1, 0, 1. Next F6, X XOR Y. So coming to the truth table of XOR, wherever if you have one value as 1, it is 1. So if you A value or B value, either of them is 1, the output will be 1. In all the remaining conditions, it is 0. So the same thing is applied here for a function f6. So for function f6, since this is both are zeros, the output is 0. Since y value is 1, the output is 1. X value is 1, so the output is 1. So both are 1s, the output is 0. So that is f6. Coming to f7, x plus y. It just implements an addition operation on the contents of x and y. So it becomes 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 0, 1 plus 1, 1. So that is an addition operation. Next coming to F8, x plus y whole complement, which means that A and B whole complement, which is called as a NOR operation, which means we are going to perform A or B. So we are going to perform A or B and then perform a complement operation for the result. So if you look at this, F7 we have already performed A or B. So we are going to perform a complement operation for this result to get F8. So 0 becomes 1, 1 becomes 0, 1 becomes 0 and 1 becomes 0. So we are performing A or B whole complement F8. Next coming to F9, it is X XOR Y whole complement. We have already done F6 X XOR Y. So for that result, we are doing a complement operation. So that is represented by microoperation as A XOR B whole complement, which is called as exclusive NOR operation. So if you look at F6, it is XOR X A XOR Y X XOR Y. So for this, we are doing a complement operation. So it is 0. So here it becomes 1, 1, 0, 1, 0 and 0, it becomes 1. So F6 is X XOR Y. For that, you are doing a complement. So that is F9. Then next coming to F10, it is Y complement. So whatever is the value of Y, you're just making a complement. So 0, 0, 1, 0, 1. It becomes 1, 0, 1, 0. Similarly, F11, X plus Y whole complement. So first we are doing a complement of Y and then do addition with X. So that is represented by a micro operation as A or B complement. First do the B complement and perform an OR operation with B complement. That gives you the function F11. So F11, So it becomes 0 1, which means 1. 0 0 becomes 0. 1 1 becomes 1, and 1 0 becomes 1. So this is an OR operation, which is called as A or B complement operation. Next F2, it is just X complement. So whatever the value of X, 0 0 1 1, it becomes 1 1 0 0. Next, coming to F13, it is X complement plus Y. So we are doing a complement, it is nothing but A complement or B. The same thing, whatever we have done with X plus Y complement, now we are complementing the value of X and add it with Y. So that is done here is F13. So coming to F14 is XY whole complement. First we are performing XY. So F1 function is XY. So F14 is nothing but the complement of F1. So whatever is output of F1, the complement operation will be the output of F14. So it becomes, this is 0 0 0 1. If you do a complement, it becomes 1 1 1 0. So F14 is 1 1 1 0. Similarly, F15 1. So the output is all ones, set to all ones. So F15 is all ones. So this is the truth table for all the 16 logic micro operations explained in this table. So next, coming to the hardware implementation. So in order to implement the hardware of this particular logic operations, as we know, even though there are 16 logical micro operations present in the table, most computers make use of only 4 operations: AND, OR, XOR and complement. From these four logic gates only, all the other 12 operations, micro operations can be derived. So the hardware unit consists of 4 gates and a multiplexer. So the hardware if you see the hardware implementation of a one stage of a logic circuit, it consists of a 4x1 multiplexer which takes 4 bit input and gives 1 bit output, and using the 4 logic gates AND, OR, XOR and complement, these are given as an input to a multiplexer, and each gate gives one input to a multiplexer, and each gate is represented by one binary value 0, 1, 2 and 3, and the xi, x and y or a or b values are given as inputs to all the logic gates, whereas for complement it takes a value of only ai. Okay, and apart from this we also have two selection inputs s0 and s1. So if you see the function table of this particular diagram, and this multiplexer takes 4 bit input along with the two selective inputs as inputs, and it gives a 1 bit output. So you see the function table based on the values of S0 and S1. If it is 0 0, it performs an AND operation. The output will be an AND on the contents of A and B. And if it is 0 1, it performs an OR operation, and that will be an output E. And if it is 1 0, it performs an XOR operation. If both are ones, selection inputs, then it performs a complement operation. So based on these 4 logic gates, apart from out of 16 micro operations, for using 4 logic gates, all the 16 micro operations will be derived. So this is a hardware implementation of logic micro operations. So the outputs of the gates are applied as a data inputs to the multiplexers, and the two selection inputs S1 and S0 choose one of the data inputs of the multiplexer and direct its value to the outputs. So based on the selection input, whichever operation has to be performed. If the selection inputs are 0 0, then this AND operation will be performed. This will be given as an output input to the multiplexer, and we get the output of the particular AND operation. So based on the function table, based on the selection inputs, the particular micro operation will be performed by the circuit. Thank you.